Uh, Dr. Kushna, sir,
Yes, sir. Yes.
you start.
Shall we start right now?
Yes, sir. Actually, I'm going to say something about you. After that, you can start.
Okay. Please start. Please.
So, good afternoon, everybody. In the third session, we'll listen from Dr. Kushna Prasad Sadangi, Assistant Professor, Department of Chemical Engineering, Biro Surendra Sai, University of Technology, Burla. His topic is waste to energy conversion through pyrolysis technique. Pyrolysis technique. Before presenting, I must speak few lines about him. Dr. Krishna Prasad Sarangi is serving as an assistant professor in the Department of Chemical Engineering, Birasundra Sai University of Technology, Burla, Odisha. He did his PhD in chemical engineering at IIT Guwahati. He has 8 years of teaching experience. He has an expertise in the area of biofuel, especially thermocatalytic and co-conversion of biomass. Successive utilization of waste plastic for biofuel, upgrading plastic to fuels, chemical kinetics, and conversion of liquid waste to fuel, and removal of heavy metals from the wastewater. He has contributed 20 book chapters in edited books, those are scopus, and published 24 international peer-reviewed SCI journal, having more than 600 citations. His edited books on liquid biofuel, fundamentals, characterization, and application has been published by Wiley Publications in 2021. Currently, he is editing two books on bioenergy engineering and biohydrogen fuel modeling and approach in thermochemical and biological tracks in Elsevier and Taylor Sciences respectively. He has edited a special one issue on biorefinery solution for biomethanol production and processing in the Journal of Biomass Conversion and Biorefinery, Springer Natures. Some of his research contributions are also presented in various national and international conferences inside and outside of India. He is an editor of several national and international peer-reviewed journals. He is a reviewer in many SCI journals and an editor in 3 international journals. Now, sir, over to you.
Thank you, Professor Mahapatra, for inviting me in this platform. This is the first time I'm presenting for CBO1 University. So let's start. Is my screen visible?
Yes, sir, it's visible.
Am I audible clearly?
Yes, sir.
Thank you. So good afternoon to all when are all present over here. This side Dr. Krishna Prasad Sarangi from BSSUT Burla. So my topic is waste to energy conversion through pyrolysis technique. So moving towards the topic, let me tell you the outlines of this presentation, which includes introduction to the waste, the technology used to convert waste to energy, their fundamentals, and some results from my research that includes pyrolysis, co-pyrolysis, catalytic vapor cracking, catalytic pyrolysis, and the chemical kinetics for pyrolysis process. At the end, we'll summarize it. So first of all, what is waste? Waste is a substance which is discarded after primary use. We say it is worthless, defective, and these substances has no use. We say these are the waste materials. Waste is a product. Waste is a product, a substance which is no longer suited for its intended use. We say if a waste has no any importance for the use directly, then we throw it. So these waste are generated from different sources, including mining, agricultural waste, industrial waste, wastewater from different industries, household waste, some construction waste. These waste are categorized according to hazardous and non-hazardous. So this hazardous category under this all these explosive materials, gas, flammable liquids, flammable solids, which are corrosive in nature, which may infect this hazardous waste. Through pyrolysis technique, we cannot produce any energy. Then some non-hazardous wastes are there. Among them, among all the non-hazardous waste materials, some of the waste we can utilize for the production of fuel or any chemicals, but all are not. So that we have to segregate the waste properly as per their degradability. Whether the waste is degradable or it is not degradable biologically. If it is biologically degradable, then we can use it for the production of fuel chemicals through this pyrolysis technique or through the thermochemical conversion technique. Some of the non-biodegradable waste cannot be used, but some of them can be used. Okay, so these are the biodegradable waste that are generated from different sources that we can use for the production of fuels and chemicals through thermochemical conversion techniques. And these are some plastics. These are non-biodegradable, and since these are the composition of hydrocarbons, we can use it for the to get fuels or chemicals. As we know that these plastics, some of them are thermosettling, some of them are thermoplastic. Thermosettling plastic generally we do not use for the production of fuels and chemicals, but thermoplastic, these can be used. Based on their thermal degradation ability, we can use it. Also, we have to think about the emissions that comes out during the pyrolysis process. So, in general, this PVC, when we degrade it in presence of temperature, at higher temperature, it produces some dangerous gases, HCN gases, that are very hazardous, very dangerous for human being. So, without using this PVC, through pyrolysis technique, all the plastic waste can be used. So that, in which way we should think that these types of raw materials can be used through pyrolysis technique to produce fuels and chemicals. This depends on the solid bio-waste. If you are taking their carbon content, hydrogen content, and their heating value. Also, we can use waste engine oil, waste oils, waste plastics, and waste tires. These are the waste materials that are available in our environment that can be processed through pyrolysis technique to produce fuels and chemicals. So first of all, pyrolysis is a process by which we heat the substance at a higher temperature in the absence of oxygen to produce the volatiles. Some of them are condensable volatiles that we collect it as liquid fuel or liquid platform chemical, or those are non-condensable gases. Some of them are carbon monoxide, methane, hydrogen. These are non-condensable gases. We can use it, we can store it as a gaseous fuel. Then the remaining part is that stay inside the reactor, that do not get volatilized, that is your biochar. This biochar can be used as a fuel, as a adsorbent, as a soil fertilizer. Okay, so here I have shown a simple figure of a pyrolysis setup where we use nitrogen gas as an inert gas to maintain the reactor inert environment throughout this pyrolysis process. Then the generated vapors are condensed with the help of the chiller, and we can collect the liquid product. So over here it's very simple that the nitrogen gas is fed from the top and we are collecting the pyrolytic vapors from the bottom, but this can be an opposite one also. So there are various types of pyrolysis reactors are available. Also we can design as per our own view to produce fuels and chemicals based on our requirement. So then, what is co-pyrolysis? In case of pyrolysis, we use a single biomass, single waste, but in case of co-pyrolysis, multiple wastes are mixed with each other to produce fuels. Some of the biomass, then waste tire, waste plastics, it can be mixed and fed to a reactor, pyrolysis reactor, to produce high quality, higher thermal stability of your fuel. And also we can use two types of biomass. One is lignocellulosic biomass that we can take, bamboo, suppose bamboo. Also we can take some algae. If this algae is having higher extractive content, this bamboo is having higher cellulosic content. So if these two will be blended or it will be mixed to co-pyrolyze it, to pyrolyze it to produce fuels, then we can get higher amount of bio-oil yield rather than the yield of aqueous product. It also has some importance on the char quality, that since the nitrogen content in the char increases, we can use it as a bio fertilizer, and this char also can be used as a fuel and adsorbent. These are also some negative impacts, that it increases the protein and pyridine content in that. So every time, in every process, whether it is a pyrolysis process, it is a co-pyrolysis process, that we use biomass and plastics, or we can use two types of biomass to produce fuel. All the oil that we say, pyrolytic oil, that is generated, it is not a pure oil, it is a crude oil. This crude oil has to be modified, has to be upgraded to get a upgraded fuel that is having better fuel quality than the crude oil. Then that can be used further. So let's see, if biomass and plastics are co-pyrolyzed, then both the devolatilization of biomass and polymer or the plastics takes place simultaneously, then and the reaction takes place in the vapor phase, the volatile generated from the biomass and the plastics, this get reacted, then we will get aromatic compounds, aliphatic compounds, along with some amount of polyaromatic hydrocarbons. As we know, this biomass is a composition of cellulose, hemicellulose, and lignin. All these three will definitely will produce some char. Along with when we will blend the plastics and will co-pyrolyze it, the char yield also affected by the plastics, types of plastics used over there. Okay. So if you will take simple biomass, then we can understand from this particular slide that when cellulose decomposes, when cellulose cracks, it forms char along with some anhydrous sugars, some purines. If you use any acidic catalyst, then you will get aromatic compounds. Due to the polycondensation reaction, you will get the chars. So the possibility of formation of aromatic compound from cellulose, hemicellulose, and lignin is there. So during this process, when low molecular oxygenates generates, when the ring breaks, when the cellulose, hemicellulose, lignin chain breaks, it forms furans, aldehyde, alcohol, ketone, carboxylic acid, along with so many phenols. These compounds, in presence of catalyst, if you will use a catalytic pyrolysis process, these breaks and it forms some ester compounds. If the biomass is having higher amount of extractives, then we can get some acid compounds. Then these acid compounds will convert to alcohol, or it will convert to your esters, so that by using this catalytic pyrolysis of biomass, we can increase the quality of the bio. Since this thermal pyrolysis, when we do not use any kind of catalyst, then it produces so many oxygenated compounds, and these oxygenated compounds is a major cause for the lower thermal stability. It reacts and it will form water along with acids. So that we can use another polymer in that, we can blend some other polymer with respect to our need, with respect to the product we want. We can produce various chemicals. Then this is the extractive pyrolysis mechanism, where we know extractives generally present in different seed materials. If you see any kind of seed materials, the extractives are the oils, fatty acids. When it get pyrolyzed, it produces several aldehyde, ketone, acids, esters, along with several kinds of your gases, combustible gases. So when we choose the raw material, we have to choose the raw material to produce either gaseous product or liquid product. If our intention is to produce liquid product, we have to choose a extractive rich biomass or cellulose rich biomass. Because lignin content if is high, then the probability of formation of char is higher. So that we can use a pre-treatment technique, that is a delignification technique, to produce higher amount of liquid yield from the biomass. So when we conduct a pyrolysis process, we conduct this pyrolysis process at different temperature, starting from the initial temperature from 30 degrees centigrade to a higher temperature. So initially when the temperature increases, at the beginning stage, water forms. Also we can say the water removes, that is the dehydration stage. Then simultaneously what happens? Carbon monoxide, very few amount of carbon monoxide and carbon dioxide generates. The probability of formation of hydrocarbons is less at lower temperature, and when we increase the temperature, then you will see that this green part getting increased. There is the formation of hydrocarbons, volatiles, that can be condensable volatiles. And these condensable volatiles, with increase in temperature, it will convert to hydrogen and methane, so that the yield of liquid will decrease. So whenever we follow a pyrolysis process to get liquid product, we have to be very careful on the temperature at which we perform the pyrolysis process. Then, what is the research scope? These are the fundamentals that we know, we studied right now. So now, what is the research scope? That what kind of research we can perform in the pyrolysis process? So pyrolysis, as we know, it is a thermochemical conversion techniques where we take waste materials, waste biomass, waste plastics. In absence of oxygen, we produce several kind of chemicals, and we can use that as a fuel. So the waste material, first we will pyrolyze it through thermal pyrolysis process, where we can vary these parameters: temperature, fields, type, fuel blend, sweeping gas flow rate, that maintains the inert environment, whether we use any vacuum or without any gas flow. These are the process parameters we have to follow to get liquid product. Once we get the liquid product, it will be categorized on the basis of the composition based on their fuel quality. If we get the disadvantages like higher acid content, higher viscosity, low calorific value, complexity in the composition, in the chemicals compositions in that, then we can use it for distillation purpose. We can separate some of the chemicals based on their preparation or temperature to get green chemicals and fuels, or it can be blended with the conventional fuels, petrol or diesel, as per the suitability of the engine, or as per the suitability based on their engine performance and emission analysis. We can blend it at different ratio. We can check what is the engine performance of that. If we don't get a very good quality of fuel, a very good quality of pyrolytic oil, crude oil, then we have to follow, either we can go for a upgrading process or we can go for a catalytic process. So this catalytic process, generally we can go for an in situ process or we can go for an ex situ process. And the catalyst that we use, we can take the catalyst available in the market like calcium oxide, magnesium oxide, iron oxide, clay, some kind of kaolin. What are the cheapest catalysts that are available with us? We can take, or we can synthesize some noble catalyst, some metal catalyst. We can do some metal, some carbon, then we can use it as a catalyst for catalytic cracking or catalytic pyrolysis process. When we use the catalyst with the biomass, that means when we mix the catalyst with the biomass and for the pyrolysis process, then we say this is a in situ process. But when the catalyst is used in a bed, that means in this reactor, one reactor biomass or the feed will be get paralyzed, and the generated vapor will pass through a bed of reactor. With a bed, of catalyst, reactor having a bed of catalyst. Then water will pass through a catalyst bed, catalytic bed, and in water phase, the catalytic reaction will take place. You will get the catalytic oil. Then further, all the processes we have to follow. And here, in this in situ process, only we can use the parameter that is feed to catalytic ratio. Then along with these all parameters we can follow, but in case of ex situ process, we can change the bed height, we can change the temperature, we can use single catalyst or multiple catalyst, then feed to catalytic ratio. By this way, we can do the research in the area of bioanalysis, in the area of biomass analysis. Then the advanced part is your upgrading of pyrolytic oil. So why we need to upgrade the pyrolytic oil? That means once pyrolytic oil is generated, is formed, as we collected the pyrolytic oil, this pyrolytic oil will be taken for their to enhance their stability, to reduce the oxygen content, reduce the nitrogen content, or to enhance the hydrogen to carbon ratio, so that it can be useful in engine. As our intention is to use this as a fuel, so we have to follow the upgrading process. So these are the limitations that I say. The pyrolytic oil, thermal pyrolytic oil, that is having lower heating value due to the higher oxygen content, elevated water content, nitrogen contents, higher viscosity due to the presence of acids, corrosiveness, then their complexity in compositions. So these are the limitations, the disadvantages of the thermal pyrolytic oil that we generated. So that we have to go for upgrading process. This upgrading process includes emulsion, hydrogenation, steam reforming, catalytic cracking, alcoholysis, then supercritical fluid extraction, molecular distillation, or emulsion in presence of ultrasonic wave or ultrasonication emulsion type and hydrotreating. These are the possible ways that we can follow to upgrade the thermal pyrolytic oil. Okay, so now when we do an experiment of biomass pyrolysis, we will get a liquid that consists of some aqueous layer and some oil layer. This density is lesser than this, and this bottom oil we have collected over here. This is not oil. It is mostly consists of water content along with some water soluble chemicals. Maybe alcohol is there, some water soluble chemicals. And the top one, it is the oil part. And to get a higher amount of this oil having higher calorific value than this aqueous product, we have to select a particular biomass. So now this is well soluble with either petrol or diesel, but this is not soluble. When we take a ligocellulosic biomass, you will get a liquid like this, and the heavier part is the oil that you will get. This is the heavier part. But in most of the cases, of higher oxygenated liquid we will get from the pyrolysis of ligocellulosic biomass. So, since the availability of the grass, wood, then sugar cane, baggage, so many things are there available easily in the environment. So, if we will use it for the production of fuel, this contains lower amount of hydrocarbon in that. But can we throw it? Because our intention is to use it as a fuel for the production of chemicals. We cannot throw it. Either we will go for other upgrading technique, or we can go for emulsification process in presence of ultrasonication, in presence of catalyst, in presence of alcohol, that we can use it to decrease the to decrease the viscosity and in presence of some surfactant to get a stable emulsion and inside the diesel or petrol. If you blend it in diesel, then we will get a diesel plus pylitic oil. The pylitic oil blended with diesel at a particular ratio of surfactant and your co-solvent. And the advantages is that it decreases the CO emissions by 75% when we use it in the combustion engine. Disadvantages: each and every process is having some disadvantages. So when we go for emulsification process, then these are the characterization that we have to follow to get the research or to find out the quality of the blended fuel or quality of the emulsified fuel. Ultrasonication we can use it. Ultrasonication we can use it to make a stable emulsion, very fine particles emissions. Okay. Then when we go for steam reforming process, as we know, when we go for reforming process, these naphthalene compounds get converted into aromatic compounds, and these aromatic compounds is a better solvent that you can use, that you can blend it with petrol to enhance the octane number. Now, in this steam reforming process, this is either a single step operation or it is a multi-step operation. That means if we use any normal catalyst, metal catalyst, then this is a single step operation, and this depends on the quality of the pylitic oil. If the pylitic oil that we use is having higher sulfur content, then you cannot take this nickel, molybdenum, cobalt, palladium, iridium, these catalysts, because they are prone to poisoning, sulfur poisoning. In this case, we can use any catalyst like dolomite catalyst, zeolite catalyst, the first stage. The next stage we can use the noble catalyst, metal catalyst at a ratio of steam to carbon ratio of 12, and higher temperature and lower space velocity, we can get the product that is your gas liquid with a byproduct of carbon dioxide. Here, this is only one process. Steam reforming is only one process that you will get a 75 to 78% of hydrogen yield with a lower composition of carbon monoxide and methane. This depends on the steam to carbon ratio and the temperature that we use with a variation of the catalyst percentage. Then catalytic cracking. Just now we have discussed in the beginning what is catalytic cracking. This catalytic cracking can be a fixed bed process, can be a fluidized bed process. In this process, what happens? We paralyze either in situ process or by following ex situ process at a temperature of about 450 to 600 degrees centigrade to get a high quality fuel, high quality pylitic oil, then gasoline, diesel, kerosene. These are the liquid fractions along with the coke. So coke is formed in catalytic pyrolysis process, also in steam reforming process it is there. In this catalytic cracking process, it is very difficult to break the aromatic ring. So aromatic ring or aromatic compounds present in the pylitic oil does not break. Although we can say during catalytic cracking process aromatic compounds get formed. These are very stable compounds. To break these aromatic compounds, we can go for this steam reforming process. So first or hydrogenation process. These two processes we can use. to break this aromatically. First, it will try to attract the hydrogens, then it will break, the ring will open. You will get straight chain alkynes, your saturated alkenes, including straight chain and cycloalkenes, you will get. So over here, the best advantage is that it removes oxygens in the form of carbon monoxide and carbon dioxide. This carbon monoxide can be utilized as fuel. Okay, it decreases the density, viscosity, and water content since oxygen is get removed over here in the form of water. Also, this catalytic cracking converts these acids present in the pyrolytic oil to esters. But it is very difficult to break or to convert these aldehyde compounds present in the pyrolytic oil. Okay, so this will be this aldehydes. If you want to decrease the concentration, break it, and we can convert it into different alcohols, different other hydrocarbons. We can follow some other processes. So this process is your supercritical process, supercritical fluid process. Over here we can use this ethanol, water, methanol, butanol at a higher temperature and pressure than the critical point. We can upgrade it. We can reduce the concentration of nitrogen and oxygen up to 50% in presence of some noble catalyst. Okay. But this is the hydrogenation is the process where we can reduce the content of saturated olefins to form carboxylic acids. Then it will convert to alcohol, and once it gets converted to alcohol, then esterification reaction occurs, decarbonization reaction occurs, then polymerization reaction occurs to get upgraded fuel oil with higher stability and char compounds. However, this is one easy process. That means we will just add some catalyst and some alcohol with the pyrolytic oil, and the acid present in that it will convert to ester and water. In this case, this reaction takes place at lower temperature. Based on the temperature, based on the types of catalyst and the ratio of ethanol that we, or the solvent that we take, or you can say some alcohol that we can take for esterification process, the reaction occurs. So we can take acid catalyst, we can take base catalyst, but in case of acid catalyst, the conversion is better due to the it is proton ability. Okay. So this process, what happens? This process only converts this acids to ester, and the yield, the selectivity get reduced if aldehyde is present in that. So that first we will convert this aldehyde to acids with ozone oxidation reaction process. Then it will then we will follow this esterification process to increase reduce the acidity, to increase the what you can say pH from acid to base level, or you can neutralize also. Then, but this process don't have any effect on the reduction of nitrogen. For the reduction of nitrogen, this process supercritical fluid extraction is good. So these are some techniques that we can upgrade the pyrolytic oil. But if you want to just separate different products, different chemicals from this pyrolytic oil, then we can follow the molecular distillation process, by which we can remove the carboxylic acid, water, some other chemicals at a very at a higher vacuum environment. But this is the energy consumption process. So also you can follow atmospheric distillation, vacuum distillation processes, flash distillation processes from this. But the question is right now, once we read that, once we know that different upgrading techniques are available, then how to select which upgrading techniques we should follow to get a better pyrolytic oil, better crude oil that we can use it the engine which is available. That actually depends on our need, what we need, and that depends on the composition of the pyrolytic oil. And once we follow any of the upgrading techniques, what is the yield of the oil? And once we get the oil, then what is the application of that? And the cost of production. So based on that, we have to select which upgrading technique we have to follow. So when we start the research and pyrolysis, the first thing we have to select the biomass. Which type of biomass we'll select? Either this is a lignocellulosic biomass, we can select algae, we can select seeds, we can select seed cakes or de-oil cakes or different plastics, what kind of plastics. Then what to do? Once we have selected the biomass types, then we will follow to characterize the feed materials. Whether it is a biomass or it is a plastic, we have to characterize it. Once you are getting characterized, we will understand what is the thermal stability of that and what point this particular feed materials get degraded, so that we can choose the pyrolytic temperature at which we will pyrolyze it to get higher amount of liquid yield rather than the gas yield and char yield. So that we have to optimize the process parameters in a pyrolysis setup. Once we get the product in the form of pyrolytic oil, char and non-condensable gas, we can categorize it, and then we will find out what are the limitations of the products, and we will follow the upgrading techniques. We can find out the pyrolytic kinetics, pyrolysis kinetics. We can find out what is the thermodynamic parameters associated with that, so that we can design, we can go for the modeling of the pyrolysis reactor by using several softwares, and then finally applications. So in the first time, let's move towards the research that I have done till now. First, we will select the raw materials. After that, we will characterize it. How to characterize? If we are taking, suppose in case I have taken one seed material, this seed material is having higher amount of extractive. So to understand, to check the probability of formation of higher amount of liquid product rather than the aqueous product, we have chosen this raw material. These seed materials are non-edible seeds. We cannot take some edible seed because it will directly affect our food chain. We cannot take that. We will take the non-edible seed materials. Then we will try to grind it. During this process, we have to be very careful that the oil should not come out. It should not there should not be any loss of oil in that during grinding process. Then we have to dry it. Then we will determine what is the moisture content over here, followed by some ASTM standard methods. Then we can determine the extractive present in that, followed by the substrate extraction process. By using solvent extraction process, we can determine the extractive content in that. Then we will get two types of product. One is your extractive free product, another one is extractive. The individual sample extractive free. That means only it contains cellulose, hemicellulose, and if some lignin content is present, then we will get the material. That is the extractive free material. Then extractives, that is the fatty acids, oligomers, compounds present in that. So these two can be individually get pyrolyzed to get the product, or after the extraction of the individual, we can see what is the yield of pyrolytic oil. Once we know the thermal degradation range, this thermal degradation range generally we get with the help of the thermogravimetric analysis process, and this process also helps us to determine the compositions like cellulose, hemicellulose, and lignin based on their temperature of degradation. Then this sun-dried or oven-dried raw materials, feed samples will be taken to know the crystallinity index through XRD technique. It will give you if it is whether the cellulose present in that it is crystalline, or this is amorphous, because the crystalline material is having higher thermal degradation ability. So you have to go for this to check it. Then we can go for the physiochemical characterization like proximate and ultimate analysis. Also, you can find out the calorific value which are related to the pyrolysis process. Okay. Then we can confirm the presence of cellulose, hemicellulose, lignin, extractive contents present in the biomass followed by FTIR, Fourier transform infrared spectroscopy analysis. Finally, if this is a biomass sample, definitely it contains some amount of mineral compounds over there. We can analyze it by using EDX analysis. These are the raw material characterization techniques. Then we can characterize the pyrolysis product. If it is a liquid product, then we can use, determine the calorific value, viscosity, pH, water content, plus 5.4 point, distillation temperature, the functional group present in that, then the cold flow properties using differential scanning, calorimetry technique, and the composition of the pyrolytic oil by using GCMS and CHNS analysis. By using this characterization techniques, we can find out the limitations. Then we can select which process we have to follow next to upgrade the biofuel. If somebody wants to start the research on biomass pyrolysis or plastic pyrolysis, this is the best way to understand what to do. If somebody is doing PhD, then what should do in the different state. The first step of the pyrolysis before moving towards the experimental setup, we have to check the degradation ability of the individual biomass through thermogravimetric analysis. Once you will take a minimum amount of sample, like 5 milligram of samples, we will keep it in a crucible in this pyrolysis setup on the furnace. Then we will increase the temperature from the 30 degrees centigrade, the environmental temperature, to a higher temperature according to the conditions of the pyrolysis setup. If we move to a higher temperature, we will see that the degradation of the sample. This is the degradation of the sample. This is the TGA graph, thermogravimetric graph. But from this graph, it is not well known that we cannot find any particular degradation stage, whether cellulose is degrading, whether hemicellulose is degrading, or lignin is degrading over here, because we do not have the individual components of the biomass. We are taking a biomass, it contains cellulose, hemicellulose, lignin, extractive, everything it has. For that process, first of all, if we have a pure cellulose, hemicellulose, lignin compound, we will go for the thermogravimetric analysis. We will find out the peak. This is the DTA and the DTG analysis. DTG analysis, this peaks. This peak shows that at what temperature the degradation starts and what temperature degradation ends. This is the degradation part or the degradation temperature for hemicellulose. This black thick line is for lignin. Then this dotted line is for cellulose, which shows that hemicellulose degrades first, then cellulose degrades. But this lignin, the degradation temperature is in a wide range. Lignin degradation occurs in a wide range of temperature, started from the lower temperature to a very high temperature. So that this TGA is most important. Although we can determine the thermal degradation temperature of the individual biomass, we can use it for the proximate analysis or to determine the moisture, volatile, fixed carbon, and ash content in the feedstock. So for that process, what to do? The same procedure we will maintain. We will take some amount of raw material, keep it inside the TGA analysis, but we have to program it properly. How to program it? First of all, we will program it that the temperature will increase from 30 degrees centigrade or the environment temperature, room temperature, to at least 100 degrees centigrade, and we will keep some residence time for some time 15 minutes. Then whatever the degradation or the evaporation takes place, it will give you the moisture content. And next program will be after 15 minutes, we will give the program to increase the temperature up to around 600 degrees centigrade, and residence time is 30 degrees centigrade. Then we will determine the volatile matter content in that. And it is most important that to determine the moisture content and volatile matter content inside this in the feed biomass, it depends on the inert gas flow rate or inert gas that we use. We cannot use oxygen, we cannot use other things. Either we will use carbon dioxide or nitrogen over here. But after this, after determination of the volatile matter, to determine the fixed carbon content, we have to burn the carbon that is present over there after the removal of volatile matter and moisture, so that the flow of the sweeping gas we can change from carbon dioxide to air. For 30 minutes we will perform the experiments. Then the change in the mass will give you the fixed carbon content. Then the remaining will give you the mass content. So this is one technique, the analytical technique by which you can follow. We can get this proximate analysis of biomass or any kind of feed sample you are taking, if it is thermally degradable. Now, I'll show you one thing. That suppose I have chosen the raw material, that is some kind of seed, corundum or one linseed. I will perform the TG analysis from 30 degrees centigrade to around 700 degrees centigrade at a heating rate of 10, 20, 30, 40, 50. What is possible at a higher rate? What is possible? We can choose the heating rate. We can select the flow rate of nitrogen or the flow rate of argon, flow rate of helium, but not carbon dioxide, not air. We can select it. Then we will perform the experiment. Then you will get the mass loss curve like this. But from here, only change in the curve we can observe it that it shows. This is the first stage, then second stage, and third stage. That shows that this is the maximum zone where degradation takes place. Degradation of the particular biomass takes place. That is, we can say that this is the pyrolytic zone. And if we perform the pyrolysis experiment, then we have to use or we can pyrolyze the feed beyond 400 degrees centigrade, so that we will get some product, liquid product. Otherwise, the yield of liquid product will be less, and the yield of char and non-condensable gases will be higher. Now, since this is not well understood from this TGA curve, we can go for DTG curve. Over here, you can see 2 to 3 peaks are available. This is due to the presence of the cellulose, hemicellulose, lignin, extractive content in that. But this, how much present in that, we can say by looking at this curve. Okay. Suppose for the pure component. For the pure component, at what is the temperature range? We can select it. Then we can see the data. We can find out what is the change in the mass in this temperature range. Then we can see this much amount of hemicellulose, cellulose, and lignin may present in this raw material. But as we see from this slide, that to determine the cellulose, hemicellulose, lignin content, we have to find out the extractive free sample. Whether we select lignocellulosic biomass, whether we select extractive rich biomass, does not depend. We have to anyhow, we have to extract. If pure amount of extractive is present over there, we have to remove it through solvent extraction technique. After that, this extractive free solid samples will be taken for the determination of cellulose, hemicellulose, and lignin. Now you see over here when no extraction of fatty acids, no extraction of extractives is done initially, then how this DTA graph looks like. Then how this DTG graph looks like, how this DTG graph looks like once we are using a extractive free sample. We are getting some peaks over here, but it is not present over here. And you see the overlapping of the curves, but we are getting overlapping of the curves, but it's very small. We can notify three stages of degradation by looking this: first stage, second stage, and third stage of degradation. This is the one technique that you can determine that to get higher amount of oil, how at what stage how much degradation takes place by looking at looking towards the rate of degradation with respect to different temperature. Okay, so this is one literature data I am showing over here. You see some lignocellulose biomass they have taken. They have shown what is the first step of degradation zone. There is the second step of degradation zone. These are some non-lignocellulosic biomass. They have taken some algae kind of material. Then they have shown what is the degradation zone. You see, this lignocellulosic biomass degradation is higher temperature, takes place at a higher temperature rather than other. Okay. Now, from the physicochemical characterization, we can get that what is the moisture, volatile ash, and pitch carbon content over there, which shows if the moisture content is less than 10%, we can use it for the production of fuel oil through or pyrolytic oil through pyrolysis process. If volatile matter content is high, it will give you higher amount of hydrocarbon. If pitch carbon content is high, it will give you higher amount of char. And ash content, if the amount is higher, that shows that it contains lots of mineral compounds which actually depends on the plant origin where it grows. Even if the movers is correct, then I just say whatever the process, whatever the raw material I have used for the for characterization purpose, I have collected suppose from Budla itself. Then if you collect from Bhubaneswar, this composition will vary because it depends on the plant where it grows. So first of all, physical chemical characterization we have to do. Then we have to go for ultimate analysis, which will give you the carbon, hydrogen, nitrogen, oxygen, and sulfur content. In that, you see this type of biomass also contains fewer amount of sulfur, so that the possibility of getting sulfur compounds in the pyrolytic is there. Also, we can get the sulfur may form sulfur dioxide during the pyrolysis process. In the gaseous phase, it may release. Okay. Then this pyrolysis actually not only we can use this biomass and pyrolysis, we can use also some coal. Coal, Indian coal, you know that low rank coal. This low rank coal, the degradation ability is very less. If we want to go for the use of as a fuel, so that what we will do if we will prepare some coke kind of material. By using a blending of biomass, then the presence of alkaline earth metals, these elements present over there, it will help in degradation of the coal. And also we can go for pyrolysis. Also we can go for gasification process to produce higher amount of hydrogen, higher gaseous products over there. Simultaneously, with a enhanced quality of the coke that can be used for as a fuel. Okay. Now this is a Van Kerven diagram by which we can observe that once you have the hydrogen to carbon ratio, you have the oxygen to carbon ratio. By looking towards this, we can say that which raw material is having higher heating value, so that it will give you higher amount of liquid product rather than others. But this also depends on the process of pyrolysis, depends on all the parameters. Okay. So if it is having lower oxygen to carbon ratio and higher H by C ratio, then we can say this thing, the heating value is higher over here. Okay. Then if you talk about some other raw materials like plastic and waste engine oil, waste motor oil, which can be used as a feedstock for the process of for the production of fuel oil, then we have to characterize it in this way. You know that this plastic contains higher amount of volatile materials, as this contains hydrogen and carbon in most of the cases, and less amount of very less or minimum or zero negligible amount of moisture with a low amount of ash content in that. So it can be used depending upon their thermal degradability, depending on the what kind of biomass we are choosing. Then we have to check it. We can take the raw material, we can blend it in different proportions. We can get the fuel oil, we can analyze it. Then we think about the upgrading procedure. Then the waste engine oil, you know that waste engine oil, every service center, motor engine oil, we use the engine oil, lubricating oil. These waste oils are generally the base oil is the synthetic oil that for to enhance the fluidability, to enhance the viscosity, enhance the properties. We have to use several kinds of additives in that so that we can meet the requirement of the engine that where it will be used. So initially, to some amount of metal contents in the form of additives, we use it. But during the engine operation, during the aging time, during the when your wear and tears occurs, so many metal components get added with this oil. Then after some time, the color of the engine oil will change. Then also the cooling property will decrease, the lubricating property will decrease, so that every time interval we just change the engine oil. That engine oil is the best source to produce fuel oil through pyrolysis process. After the removal, either after the removal of all the metal contents, or without extraction of all these heavy metal contents, we can check it whether this heavy metal concentration is getting degraded or we are getting reduced through pyrolysis process. We can check it. Now, when we talk about the co-pyrolysis process, always we'll think about what is the degradation temperature, so that we can blend it with the biomass. So when we talk about the biomass, first of all, you see so many plastics TG analysis is showing over here, including the coking coal. You can see PVC, whether PVC is getting degraded with a lower temperature than PS, PET, PPE, and the hard coking coal is having higher thermal stability because higher thermal stability, right? So based on the thermal degradation temperature, we can select which raw material we can choose and with whom we are blending. If you will blend with motor oil, if you will blend the plastic with motor oil, then we will see that what is the degradation range. If it is coming within the range of the motor oil or LDP, if we choose that motor oil is the base oil, and we will blend the plastics. Then, since the base oil is motor oil, our intention is to enhance the quality of the pyretic oil that is produced from motor oil, then we will blend the plastics with a different percentage. So these two feed materials, degradation temperature should be identical. Or we can say that since the base material is motor oil, or if the base material is biomass also, the plastic that we choose, it should degradable within that temperature range. Otherwise, plastic biomass will get paralyzed, plastic will be there inside this reactor. So that depending on the thermal ability, thermal stability of individual feedstock, we have to choose the raw material. Here I have shown for motor oil, it is shown from used oil. When we blend the used oil with LDP, when you blend motor oil with LDP, also when we blend with plastic with sawdust, so we have to choose which temperature range we have to follow. Okay. Here in this graph, it is well known. You see blends. Blends. The peak height is lesser than the PVC, and it is higher than the waste sawdust. Okay. So peak height shows the peak temperature. At higher temperature, higher residence time. It will take more time at that particular temperature to get degraded. If peak height is low, then easily it will degrade within that temperature. It will take low time for the degradation. We have to observe in this way. Then, when we go for co-pyrolysis for thermal decomposition of waste plastics biomass with respect to different temperature, we can determine what is the composition of the biofuel or composition of the pyrolytic oil. So initially, due to dehydration of this water, we will get water. Then hemicellulose decomposition will give you acids, aldehydes, some amount of furan, some oxygenated compounds. And we know that hemicellulose is lower thermal stability than cellulose. So first hemicellulose will degrade, simultaneously cellulose will get decomposed, then it will form furans, anhydrous sugars, some amount of aromatic compounds. Also, when we blend it, when we blend the material, the plastic material, then it will form, if polystyrene is there, then it will form styrene along with some amount of polyaromatic hydrocarbons along with some amount of esters. Okay, so these are the temperature range by which you can get the product. If we conduct the experiment up to 200 degrees centigrade with a co-pyrolysis process, then we can expect this kind of liquid product must be present. This kind of composition must be there. So according to different temperature zone, we can select, we can observe, we can analyze the liquid sample we will get. We can say that this should be there. This chemical should be present in this pyrolytic oil. Okay. Now, from the pyrolysis point of view, when we go for the thermal pyrolysis process, first of all, we should see that what is the yield of pyrolytic oil, because our intention is to produce pyrolytic oil, not the char or not the gas. So we have to perform the experiment at different temperature at a particular heating rate. We can change the heating rate, we can change the sweeping gas flow rate. Okay, and we have to find out what is the optimum temperature at which the yield of pyrolytic oil is higher. Now, three graphs all are same. You see, this is the for mohua seed. You see that 525 degrees centigrade is the highest temperature, or sorry, lowest temperature at which we are getting a higher amount of oil yield. But when we talk about the Niger seed and Karanga seed, we are getting at 550 degrees centigrade, which shows that different biomass behaves differently, and the degradation temperature is, since the degradation temperature is different, since the composition is different, and the kind of extractors present in the different mineral compound is different. Whether we follow the same thermal degradation procedure, the yield will vary and the temperature at which we get maximum yield of pyrolytic oil will vary. Now, when we talk about a catalytic process, whether the yield of oil is better, or the amount of oil we will get in catalytic pyrolysis oil is in higher amount? No, it is not higher amount. Catalyst, definitely, when we talk about catalyst, we say it enhances the rate of reaction. Definitely, the yield of pyrolytic oil will be higher. But very few cases, the yield of pyrolytic oil is higher. But almost all, the yield of pyrolytic is mostly same with the thermal pyrolysis process. Also, we can say that due to the catalytic poisoning, if we are using in situ process, the yield of pyrolytic oil will be lower than the thermal pyrolysis process. So when we use any catalyst for in situ process, we can blend it, we can mix the catalyst with the biomass, like in different ratios. Suppose I can say 2:1, 4:1, 18:1 ratio, different ratio, 3 ratios I have shown over here. You can choose very low ratios also. So you see over here that with respect to the change in the amount of catalyst in this feedstock, the yield of oil, tar, gas varies. So suppose I say over here that this is the higher amount of the yield of oil when we use calcium oxide as a catalyst at a ratio of 2:1. That means what? 2:1 is a very higher ratio of catalyst. Ratio of catalyst is very higher over here. Okay, so there is no point that we can use a very high amount of catalyst for getting a upgraded fuel, upgraded pyrolytic oil. in all the cases you see that the yield of pyretic oil is higher at higher ratio. Somewhere over here you see at a lower ratio, 8:1 ratio, yield of oil is higher. But for the case of calcium oxide, it is somehow different. That means at a higher catalyst ratio only, if you use calcium oxide as a catalyst, then it will give you higher yield of oil. Total liquid means is a mixture of, as I saw before, it is a mixture of aqueous product and the oil. It is a mixture. This is your total oil, and this is only the oil yield. Oil means higher amount of hydrocarbon present over there. Okay. Now we will go for the co-pyrolysis process. We will see what is the yield of the pyretic oil and yield of the char and gas. So how will we use it? We will just add the waste plastics. Suppose I have taken polystyrene, because polystyrene is the thermocols are we are throwing everywhere after using it. I just try to use it for co-pyrolysis process to see whether it is having an effective quality to enhance the quality, enhance the yield of pyretic oil, enhance the decrease the char ability, char formation ability, and check it. What I observe when we compare with the thermal pyrolysis process, you can see over here that the yield, as we add polystyrene with the feed materials, it increases the yield, and simultaneously it decreases the yield of char. With go on increasing in the ratio, the char yield decreases. That means when we co-pyrolyze the mahua seed with polystyrene, it helps in the degradation of the mahua seed. That's why the char yield decreases. Otherwise, it could be increased. Every case it is like that. Simultaneously, you see the yield of non-condensable gas is also lower. That means more amount of condensable volatiles, condensable hydrocarbons generates when we co-pyrolyze with plastics. One plastics I have shown over here. It's not possible to show all the results that I am having, but one only I am telling you. You can follow publications, different publications, to know what is the effect of everything. Sometimes also you can take some SDP. But SDP, when we pyrolyze it, we will not get the oil. We will get some kind of wax kind of material. So for that process, we cannot pyrolyze with biomass, because when we go for the co-pyrolysis process, we will not get liquid product. We will get wax product. That means it does not crack properly. Okay. So now we will go to see what is the effect of thermal pyrolysis on the fuel properties, like calorific value, density, viscosity, flash, fire, pore, cloud, water content, pH, and that. So you see over here, it is having a higher viscosity than diesel, so that you cannot use it directly as a diesel fuel. Density is mostly similar, and calorific value is lower than this, but very close to this, 40 megajoule per kg, 41 megajoule per kg. Right now, since different kinds of biomass we used over here, you can see that distillation temperature also varies. So that we can say that when we change the raw material, then the composition of the feed will composition of the product will also change. Accordingly, the distillation temperature will also change. Now, what we will do, we will go for a catalytic process. We will go for a catalytic process to study the effect on different fuel properties like viscosity, pH, calorific value, water content. Now you see when we use the catalyst at this ratio actually chosen based on the yield of oil. When we get the higher amount of oil, we have chosen that ratio. Then we have studied this fuel properties. You can see when we use catalyst over here compared to thermal, the viscosity is less. pH from the acid to base, it shifts. Then the calorific value changes, but little bit it changes. Water content, definitely it is higher in this pyrolytic oil, because during this catalytic process deoxygenation takes place. Dehydration is definitely there, but deoxygenation process converts converts this oxygen content present in that to form water. Now the question, what is it? It is 0.32 and it is 0.65. It is not that much higher. No, it is higher. And where? Because as water is water formed over there, it will be separated easily. So this small amount of water contents remains inside this pyrolytic oil in the form of microemulsions. It is very difficult to remove. Okay, so now you can see over here from this graph that with the use of calcium oxide as a catalyst at different ratio, how the viscosity gets changed. So lower ratio of calcium oxide when you use, it decreases the viscosity from a very high to low. So that we can think about a catalytic process, but this is the in situ process. Okay, we will see in further what is there. Okay, now when we talk about a co-pyrolysis process, then the comparison between the fuel properties, it is in front of you. What is this? When we blend it at different, when we blend the polystyrene, this thermocol at different ratio, 1:1, 2:1, 4:1, 8:1, from lower ratios to higher ratio, we see that a ratio of about 2:1, we are getting a reduction in the viscosity from 33.98 to 5.28 centipoise. Along with this pH get in the positive side towards the lower, you can say higher pH. Okay, then calorific value increased from 41 to 43.36, and with a formation of zero amount of water. And this kind of effect we see when we choose different kinds of raw material. So we observe that 2:1 is the optimum ratio of polystyrene that you can add with the same kind of material to get lower viscous oil with a lower acidic oil with a higher calorific value, which is mostly close with the diesel fuel. Now the question is that when we increase, suppose beyond 2.1, 2:1 to 1:1 will go, then what will happen? Definitely viscosity is again reducing. Then what happens for the calorific value? Why calorific value get reduced? That means when we use polystyrene as a co-feed in that, definitely it forms styrene along with many kinds of polyaromatic hydrocarbons, including naphthalene, so many. These aromatic compounds are does not burn easily. It will give you some unburned hydrocarbons when we burn it. For that purpose, we will go for a carbon residue test. How much carbon residue is present over there? Now we will go for a 2:1 ratio, 1:1 ratio. So carbon residue we are getting 3.48% in 1:1 ratio at higher ratio, and it is lower than the 2:1 ratio, and it is definitely higher than the thermal pyrolytic oil. Now the question is, if it is lower than the if the thermal pyrolytic oil carbon residue is lower, then it should give higher amount of calorific value. No, because this contains higher amount of oxygen. Because of the oxygen, the calorific value reduces. Because of the presence of acids over there, during the combustion process, it forms water. So the calorific value is lower over here. And this is well understood and well visible when we go for a calorific value test by using a bomb calorimeter. You can see this. What are the shoots present over here? These are the source, because when the polyaromatic hydrocarbon is present in a fuel, after combustion it will give you higher amount of soot over there. It is well understood. From this pan it is there, everywhere it is well understood. Okay. Now, to know about the effect of the blending in copalysis process and the effect of the catalytic pyrolysis process on the cold flow property, or to understand the amount of presence of saturated and unsaturated hydrocarbons in that, we can go for a differential scanning calorimetric analysis. By using it, if you compare with this, you can see this graph over here, right hand side. Now, thermal pyrolytic oil DS analysis is there, waste polystyrene pyrolytic oil DS analysis is there, along with the co-pyrolytic oil where at 2:1 ratio it is there. What we are getting, that two peaks represents composition of two compounds. Two means saturated and unsaturated compounds. These two peaks we are getting over here, we are also getting over here. We are not considering over it. When we go for a DSC analysis, we have to increase the temperature from initially we have to decrease the temperature from 0 to minus, then again we will come to minus to 0 to again to higher temperature to observe the pour point, to observe the crystallization temperature of the oil that we use. Because if it contains higher amount of some alkane kind of thing with a long chain hydrocarbon, then melting point is higher. If melting point is higher over there, we cannot use it as a fuel. We have to reduce the melting point on that. So everywhere you can see that small peak means low amount of saturated hydrocarbon with a long chain hydrocarbon, and this represented with a higher amount of short chain hydrocarbons. So this analysis is very well analytical technique to understand the composition based on the saturated hydrocarbons or unsaturated hydrocarbons present in that. Saturated means only single chain hydrocarbons. If we are adding any double bonds over there, then multiple bonds will be present, so it will be unsaturated hydrocarbons. Based on that, actually this saturation and unsaturation of unsaturated hydrocarbons present in that, it decides the pour point of the oil. This is most important for the analysis of the fuel. Now, when we talk about the production of aqueous phase and oil phase in catalytic pyrolysis process, is well understood. You see that once we talk about catalytic process, definitely deoxygenation takes place. Due to the deoxygenation process, water forms. The water, very few amount is present inside this oil that in the form of emulsion, micro emulsions, and most of them are getting separated over here. So you can see that the water content, when we talk about a catalytic process, the water content in this high density pyrolytic oil that we get is getting increased with a lower catalytic ratio, and in the oil also it is higher. Okay, so by this way we can analyze the pyrolytic oil to get the product. Now, if you talk catalyst on distillation temperature, you can see each and every catalytic ratio over here. The distillation varies, distillation temperature varies, because when we do the distillation experiment of diesel, maximum within 350 degrees centigrade, all the fractions will be removed. So based on that, we can say up to 40%. The thermally, you see the temperature is higher over here, and it is lower than that. Again, it is higher. Again, it is higher. So based on our requirement, we cannot say that this is the optimum catalytic yield where we will get the best product. We cannot say like this. Best in the form of what? Best in form of either the viscosity, in the form of fluidability in the form of cold point, pour point, calorific value, then acidity based on the composition. So nothing is a bad catalyst. Not none of the catalyst is a better catalyst. Depending upon our need, what is our intention. If we want to check the composition, accordingly we can select the raw material. So composition, when we talk about the composition effect of different catalysts, then you see over here, initial acid content is about 13% in thermal process, and when we go for catalytic process, it forms ester. It forms ester, and you see, along with some nitrile compounds, some many number of compounds are present over here. If you talk about only calcium oxide, 8:1 ratio, then you see alkanes. The concentration of alkanes is around 15%, which is more than that the thermal process. So likewise, we can analyze that which catalyst will give us what kind of liquid product. So every cases, if you compare from with the catalytic pyletic oil, the thermal pyletic oil will be compared with the catalytic one, then we can say that the increase in the concentration of alkanes, esters, nitriles are there along with higher amount of aromatic compound. That we can say that the concentration of aromatic compound is higher in catalytic process rather than thermal process. The same also we can think about in a co-pyrolysis process, that since we use polystyrene, definitely styrene will be there, aromatic compound will be higher in the pyletic oil, so that we will get the aromatic compound in the pyletic oil with a you can see over here acid content is almost 13%. Over here also it is 10%. So it has a lower effect on the acid contents, but the ester contents it is around 40% over here, and it is around 6% to 7%. So we can say that this co-pyrolysis process is a better ability to get ester compounds where number of reactions, thermal reaction reactions, so many reactions occurs to get a better quality of fuel. It will be well understood if I will show over here in the tabular form, so that initially the thermal pyletic oil, you see the component complex in nature, which is having nitrile component around 26.38, which is responsible for the lower thermal, lower stability, not thermal stability, lower stability along with lower pour point. Okay. Then when we go for a co-pyrolysis, simple, we do not use any kind of catalyst over here. We can use catalyst after the co-pyrolysis process, that we can say this is a catalytic co-pyrolysis process to observe the yield, to observe the composition of the pyletic oil over here. Okay, so over here you can see that the aromatic compounds increased from 4.87 to around 46.61% when we go for a 2:1 ratio CID to polystyrene ratio. Along with the ester concentration increased from 2% to 12%, and the reduction in the nitrile compounds from 26% to 6% we have observed, with some sulfur compounds which is present over here. It is completely zero in the co-pyrolysis process. That means whether it is sulfur get degraded? No, it is not degraded actually. Sulfur, how it will degrade? It will live in vapor phase with SO2 gas. That is also a problem. We cannot just release all the sulfur components present in this pig material. We can observe that sulfur from this process, from absorption technique. So from here, what we observe that we can go for a co-pyrolysis process with the help of plastics to produce a better quality of the fuel oil. Now, if we produce a better quality of fuel oil by using the co-pyrolysis process, what should be the thermal stability? What should be the stability of that? We have to store it for some time. For that purpose, 40 days time period was selected. Then at every 10 to 20 days, we check the viscosity, pH, density, and calorific value of that fuel. That shows that when at the 0 day, when the day it was produced, suppose the viscosity was 5.2, then pH was 5.99, and density 0.91 gram per centimeter cube, and the calorific value is 43.36 megajoules per kg. At 20 days, we saw that the calorific value is remains same. There is no change in the calorific value, but we got a change in the viscosity. The viscosity is increased over here. Then we can say during the aging time, some reaction at normal atmosphere, some reactions is going on inside that. During this process, what are the acids present in that? It may produce water. Okay, so during this 40 days time period, the viscosity varies, viscosity increased, the pH remains around 5.59 to 5.41, density decreased up to 0.85, and the calorific value reduced from 43 to 40 megajoules per kg. That means we can say that this pyretic oil is not at all stable. We can store it for a longer period of time. We have to use it immediately. But this is not the way. Immediately, the day we will produce it, we cannot use it, right? So, to know the effect on the saturation or effect on the formation of saturated and unsaturated compounds over there, again DIC analysis was followed. You see, this is the day 1 peak and the day 2 peak. So we are not getting any peak at around 5.32 degrees centigrade, so that we can say that the lower due to the increase in the chain length, we are getting a higher crystalline point, higher temperature crystalline point. Melting property increased over here. So some of the suppose initially few amount of short chain alkanes will be present, then finally we'll see the long chain alkane will be present in that. It also can be determined with the help of GCMS analysis that I have not shown over here. Another thing is that when we talk about a ex situ catalytic pyrolysis process, then that is known as catalytic vapor cracking, because the vapor that is generated from the feed material, it passed through a bed of catalyst, and the reaction takes place over there. And in this case, since the catalyst is not mixed with the biomass, the possibility of poisoning is less. Also, we can expect that lower amount of catalyst may be required to produce a better quality fuel. Also, it is well understood from our study. Suppose initially I have taken castor seed over here. Castor seed thermal pyrolysis, it gives around 70% of acids. Now, when I use the catalyst, different catalyst, calcium oxide, zinc oxide, kaolin, and different weight percent, what we observe that the yield of ester increased. Initially, what is the ester yield? 0. But when we use catalyst, the yield of ester increased and the acid content decreased, along with some amount of new components in the form of ethers, alcohols we are getting. That means and previously when we have seen that we have used the catalytic ratio at a very high ratio, 2:1 ratio, then it gives us a better quality of fuel. But right now what happens? We are using only 15% of calcium oxide. We are using 10% of zinc oxide or 15% of kaolin to get a better quality of fuel, quality of pyrolytic oil. It also able to degrade the aldehydes, nitrile components present in that. Okay. Simultaneously, you can see that other components increase in the concentration of other components also you are getting. But different catalysts are having different different activity, reactivity to produce the particular to produce a particular chemical. Okay. So now in this case, what we have done, we have taken 10, 15, 20% of catalyst. Now what we do, we do the catalytic vapor cracking process by taking a low amount of catalyst, by changing the catalytic bed height. In this process, the bed height is same, but in this process, we change the catalytic bed height to observe the effect on the fuel property along with the composition. What we saw from that, we saw by taking 1%, 2% or 3% of the catalyst, 1% of the catalyst, it is able to reduce the viscosity from a higher number to a lower number. It increases definitely, it's not good, pH of around 8.75 is not good, but the catalyst has the ability, the calcium oxide catalyst has the ability to increase the pH from acid to base, so it increased over here. And when we change the catalytic bed height, also we observe the effect of the bed height on the fuel properties. The fuel properties increased from 30 to 33, 33.67 at a 3% of catalyst. That shows that it is better always to go for a catalytic vapor cracking by using a proper bed height. For this proper process, we have to perform a lots of experiments. We have to see which is our intention, which is our need, what should we need in the pyrolytic oil, which is having higher impact on the cetane number, on the calorie value, on the viscosity. Based on that, we have to choose. Now, you see, with respect to different catalytic bed height, how the concentration of the pyrolytic changed. It affects in most of the cases from ester, then phenol components present in that, the aromatic compounds present in that. You see very nicely we are getting what is that aromatic content we are having these non-phenolic aromatic compounds. Thermal pyrolytic oil it is 3.55%. When the bed height we maintain 8.5 centimeter, it increased to 6.4, and again at 11.1 centimeter, it is 2.87. That shows what? That shows that the residence time of the vapor inside this reactor and the contact time between the catalyst and the vapor give you the quality or give you the yield of pyrolytic oil at a different composition. Okay. So here I have shown a comparison between in situ and ex situ pyrolysis process. Definitely at different ratios. Let's see. Castor thermal. All these papers are my publications only. So castor thermal initially it is 3.7 pH, but when we use castor in situ process by using not in situ, ex situ process by using 10% ZNO, 15% CaO, and 15% kaolin, we are getting increase in the pH value, simultaneously decreasing in the viscosity and increasing in the water content, increasing the calorie value, decreasing the cloud point over here. But when we talk about a catalyst in situ process, 2:1 ratio, you see how much amount of catalyst are required over here to enhance the fuel properties. So that from the study, what we observe that compared to in situ and ex situ process, we can go for ex situ process to get a better quality of fuel oil. Now, once we have the idea to get to produce fuel oil through pyrolysis process, then we can determine the kinetics of the pyrolysis, and this kinetics, this thermal degradation kinetics can be determined by using TGA analysis. First we have to perform a TG analysis. We have to determine the zone of degradation at different temperature. Then for different zone, we can determine the kinetics and thermodynamics. Okay, because every cases, this is the temperature zone at which the first step of the pyrolysis takes place, and this is actually the TG analysis of extractive free seeds. That's why this peak is higher over here. We cannot say that only moisture is present over here, because we are getting a peak at around 100 centigrade. No, because it is treated with this, some there may be some fractures, there may be some changes in the feedstock composition, so that we are getting a lower temperature peak over here. We also can say that during the treatment with alcohols or some other solvents, the stability, thermal stability get reduced. Because of that, we are getting a peak over here at lower temperature. So first of all, our duty is to look at that how many stages are there. 1, 2, 3 stages. That means 3 stages of degradation we are having. We can perform this experiment at a different temperature range and different heating rate, so that we can observe that what is the effect of heating rate on the kinetics of pyrolysis. Okay, so temperature is decided right now, then we will follow the kinetics process. So theory of kinetics says the Arrhenius law, we know that the K equals to K0 to the power minus E by RT. Then how this process will be used over here? We know that from this process that with respect to increasing temperature, the conversion increases, or we can say the degradation increases. It will, the feedstock, the solid will get devolatilized, it will give us some volatile material. That is the change in the conversion. What was initially? Initially 100% was there. Then at a temperature of about 200 degrees centigrade, suppose, sorry, not 150 degrees centigrade, suppose. Over here, what is the change in the mass? So what is the initial mass? Then the final mass. So initial mass minus change minus the mass at a particular time t divided by initial mass by the final mass will give you the conversion. How much amount what is the conversion rate with respect to a particular heating rate at a particular temperature zone, we can determine. So you can determine the x initial minus at time t divided by initial minus final, we can get a value that is your conversion. Then x, in terms of x, we can write this Arrhenius equation and we can simplify it. Take the logarithmic value, that we can get ln of minus ln 1 minus x equals to ln of k0 by beta. Beta is the heating rate over here, okay, and RT square by E minus E by RT. So over here, if we will draw a straight line versus the left side ln of minus ln 1 minus x versus 1 by t, we will get a slope which will give you the value of E by R, and the intercept value will give you over here. Then from the intercept, we can determine the rate constant k0, and from the slope we can determine the value of E. So when we plot it, we should understand whether we are getting a straight line or we are not getting a straight line. Here we have taken the order of the reaction is 1, because I have seen also so many literatures are available. You can see that biomass pyrolysis, the order, if you check the order, it will be mostly 1. So when we choose order is 1 over here, so that we can get this kind of equation. From this equation, we can draw a graph where we will get my ln of minus ln. We can get a straight line over here. You can see what I did over here. I have chosen the conversion initial from 100% to 90%. So first 10% conversion. Whether the rate of reaction or whether the order is 1, if you are getting a straight line, definitely the order is 1. If you are not getting a straight line, order is not at all equals to 1. Also, you have to see what is the R square value. If the Asper value is more than 9.3, 9.4 or 2, it is not below the 9 point, then sorry 0.9, it should not below the 0.9. Then we can say that it follows the Karpatov reaction, and whatever the kinetics we are determining, it is correct. Okay, so that initially 10%. First, what happens when the thermal degradation occurs? If we choose a biomass, we choose a raw biomass without the treatment, without the extractive removal. What happens? Initially, you will get the removal of water or removal of the moisture. That is not a degradation zone. So the kinetics will be determined only for the degradation zone, not for the evaporation zone. So the X rating over here is suppose 10%. This is beyond the evaporation zone. Beyond the evaporation zone. Okay. So first 10% we are getting a straight line over here. Then again for this 10%, 20%, 30%, 40, 50, 70, 80. This is even last up to last. But when we see this graph, what we are getting? We are getting X is equals at when conversion is 60%, we are getting a straight line up to this, but again it starts from here. It's bend. We are getting a bending line. This is not a straight line. That means from 50% to 60%, at some point the order is not one. Order is not one. For that purpose, what we need to do, we have to go for, we can change the order n value. We can see what is the line we are getting over here. Okay. Also, we can see that at 50% what is the curve we are getting. Also at 55%, then 55 to 60% what is the curve we are getting. Like that, we can say that what is the whether at what point of degradation the order is not equals to 1. And once we are getting this straight line, we can get the equations and Asper value over here, so that from the equation and Asper value, we can calculate the EA, activation energy, and the T exponential factor. If we are representing in terms of K0 or K, doesn't matter. Okay. So initially, you can see at a particular point, at around 30% conversion, the EA is higher, then it gets reduced. Again, it is increased. So that we can say that where this is the one stage, then this to this second, third stage, then fourth stage of degradation, where the activation energy changes. So getting a very high amount of activation energy. That means whether degradation takes place over there. No, degradation does not take place over there. It takes a long time, because what is the conversion? Conversion is around 80%. That means most of the volatile is getting released from the biomass, from the feed material, only remaining char or carbon, which are not volatile carbons. It is volatile, but at higher temperature it is volatile. Within the temperature that we have chosen, it is not volatile. Because of that, we are getting a higher amount of activation energy. Also, the possibility of getting negative activation energy is also there. Okay. In case of coal pyrolysis, also you will get a negative activation energy. So that was done by taking 10% conversion interval. This is done with 20% conversion interval. So 20%, first 20%, second 20%, third 20%, fourth and fifth. Now you can see everywhere we are getting a straight line. Somewhere we are deviating over here, we are deviating over here. So these 2 points, we can say that activation energy shifts, the order shifts over there. We can say that the degradation zone shifts from one temperature to another temperature zone. So we can perform this kind of kinetic analysis, kinetic study. Also, so many types of kinetics theories are there, like your Kissinger's method, OFW method. So many methods are there, distributed activation energy models. So many models are available right now. So many people are doing this kinetic study. Also, very good journals they are publishing. These are all my publications from where I have shown. Okay. So now I have chosen another raw material. What is that? This is the waste engine oil. One of my PhD scholar, also you can say that she is a faculty member from chemical engineering department. Previously, she is there in CB Raman. So Ms. Nivedita Patel, actually, she is doing PhD in this area. Right now, she has published around 6 papers. So some of them I will show over here, not all. We do not have sufficient time to show everything. But when we choose waste engine oil over here, what is that? We have received a thermogravimetric analysis like this, where within a temperature of 200 degrees centigrade, we are getting the devolatilization at around 7.94%, and beyond 450 degrees centigrade, 9.32% get degraded. But within the temperature of 200 to 450 degrees centigrade, 90.7% of waste engine oil is get get devolatilized, get removed, so that you can choose this temperature range, or you can go beyond the temperature so that you can get higher yield of pyrolytic oil. For this purpose, different temperature zone we have performed the pyrolysis, and we have received at around 550 degrees centigrade the yield of pyrolytic oil is higher over here. Since this is the waste engine oil and we do not have any maybe some pure amount of oxygen may be present over there during the handling time or storing time, but over here we have not received any kind of phase change in the pyrolytic oil. It is single pyrolytic oil we have received. Okay, so over here the yield is around 78% of yield we are getting if we take 100 kg of raw waste engine oil. We will get around 750 ml of pyrolytic oil. Then at different temperature zone, when we see what is the effect of temperature on the calorific value, we can see that at 550 degrees centigrade, where the yield of pyrolytic oil is higher, we are getting a higher calorific value pyrolytic oil, where maximum degradation occurs. That means maximum amount of HC compounds present in that get degraded. It forms some condensable liquid, and we are getting a good fuel quality, good calorific value pyrolytic oil. That is around 42.4. It is almost closer to number 2 diesel and number 2 petrol. Almost similar. But whether we can use it. So to use it in a fuel, we have to go for a fuel property comparison study with respect to the fresh engine oil, waste engine oil, and waste engine oil pyrolytic oil with diesel and gasoline. Okay, so over here what you can see, the kinematic viscosity of initial the fresh engine oil is 105 centistore, and waste engine oil, it was unpyrolized one, there is a field one, field stock, having the viscosity 23.30, and it gets reduced when we pyrolyzed, thermal pyrolyzed without using any catalyst. We have so many results in catalytic pyrolysis, catalytic co-pyrolysis, but we do not have sufficient time to show. Somehow I will show over here. All the papers are not published, some are there in the review condition, so I have not shown over here. Right now, what we can understood over here, that we can use waste engine oil pyrolysis to get pyrolytic oil to use it as a fuel in diesel engine. Then, as we know that this waste engine oil, due to the wear and tear inside this engine, due to the aging time, we are getting an addition of metal content in the engine oil. So initially, actually, we can remove it by using different washing techniques, but it will be costlier. We saw that when we pyrolyze it easily, some of the metal concentration is getting decreased by evaporating as a non-condensable gas, but not all fewer amount. You can see the chromium present in that, it is as usual same. Chromium, cobalt over here is as usual same. No changes. SR, TI, no changes in that we are getting. Also AS, but somehow we are able. Also you can see for aluminum Al, but somehow we are able to decrease the concentration of Ba, Ca, then Cu, Fe, Mg, and then some amount of Ni, Pb, almost zero. Okay, that means thermal pyrolysis, if thermal pyrolysis can decrease the metal concentration, then if you go for catalytic and co-pyrolysis, definitely it will decrease the metal concentration. Okay. So right now, if we talk about the components composition of the hydrocarbon composition of the pyrolytic oil, what we can see, the thermal pyrolytic oil, this is the waste engine oil, this is the base oil, this is the waste engine oil, pyrolytic oil, this is the feed, this is the product. We can see the straight chain alkanes is around 14%, but in case of pyrolytic, when we pyrolyze it, we are getting 32.97%. So the concentration of alkanes increased over here. Okay. Likewise, also you can see that some other components like the ethyl dimethyl benzene is getting reduced over there. Okay. Then trimethyl benzene is reduced. So we can say that the concentration of aromatic compounds get decreased over here when we go for thermal pyrolysis process. Simultaneously, the waste engine oil is having higher amount of around 6% of pH, polycyclic aromatic hydrocarbons, will also get reduced. Now, if we will go for a carbon number testing over there, what is the what number of carbon atoms present over there, then we can see this thing that we are getting a lower carbon number of hydrocarbons initially, lower carbon alkenes. That means straight chain alkenes, the concentration of straight chain alkenes increased when we pyrolyzed it. This is also one step. Okay. Now you can say that with respect to different carbon number, if we will choose that pyrolytic oil as a crude oil, then what should be the composition? How can we think about to use in a petrol engine or diesel engine or another type of fuel? How can I choose it? What we saw that it contains around 65% of gasoline, then hydrocarbon C9 to C12. Along with C11 to C15, 24%, then 7% of C15 to C19, greater than C19, 15% is present, heavy fuel oil. So we can categorize this pyrolytic oil based on the carbon number, and we can say since 65% of gasoline then hydrocarbon are present over here, we can use it in gasoline. But we should see that whether this pyrolytic oil is miscible. What is the miscibility of this pyrolytic oil in gasoline or diesel? We should see that. We have to blend it together, and then we have to store it first for at least 24 hours to 48 hours. I should say any phase separation is there or no phase separation is there. If no phase separation is there, then we can say 100% it is miscible. We can use it as a fuel by blending with gasoline. Okay, also you can distillate this crude oil to get gasoline, kerosene and diesel range hydrocarbons, fuel oils. Okay, now what to do? We have blended this waste engine pyrolytic oil with conventional diesel. Then we observe that we are able to blend from 5% to 30%. But when we saw the calorific value, you see initially the pyrolytic oil is having calorific value is 42.4 and diesel is having 45.5 megajoule per kg. That with increasing the concentration of pyrolytic oil in the diesel from 5% to 30%, at some point the calorific value is higher than it gets reduced. Then you can say, see, at 20% it is 44.34, which is lower than the diesel but close to this. And beyond that, if you will blend it with the diesel, the calorific value gets reduced, so we should not blend it. We have to think about a fuel which is having higher calorific value, lower class point, and lower viscosity, or similar to diesel. If we are using in the engine that is available right now, we are not modifying the diesel engine, we are using the same fuel in the engine that is available. Okay, now this is the result that we have obtained from blending of pyrolytic oil with diesel. Now what we will do, we will try to blend some alcohol in the pyrolytic oil. We will see whether it meets the fuel quality. That means our feed is the pyrolytic oil and we are adding the alcohol. Suppose you have chosen ethyl alcohol. So from 5% to 30% we have added it. And we saw that at around 20% addition of ethyl alcohol with the pyrrolitic oil, it gives a higher calorific value, that is 44.24, which is similar to 20% that we are adding with the diesel. And from the gasoline also, I have forgotten to give the gasoline one over here, but we have the result over here, which is also very close to this. This gasoline is having 45.8 megaliter per kg, and beyond that it reduced. The question is why it is reduced? Why it is reduced? Because what happens when we add alcohol? Alcohol is an oxygenated compound. When we add alcohol, the concentration of oxygen increases in the fuel oil, and the presence of oxygen gives us a better combustion ability, and because of that we are getting a higher calorific value. But sometimes if the concentration of oxygen will increase, then it will not give us a higher calorific value, it will give us a higher amount of water during this combustion. Because of that we have to optimize the process, we have to optimize the blending operation to get higher amount of heating value or calorific value. So that now ethanol blend we have observed at E20 we are getting a higher calorific value rather than E30 and E5. So from this what we observe that pyrolysis process is one of the thermochemical conversion technique that to convert energy, convert the waste into energy, not only the solid waste, also liquid waste. But the most important thing is the selection of the parameters that we decide. If we decide the yield of oil, if we decide the yield of pyrolytic gas or char, or decide if we decide that suppose our intention is to produce only ester compound, then we can choose a particular catalyst, we can see it. Then the upgrading techniques which we need to follow to get a particular quality of fuel, depends on that we can select the upgrading techniques, and this is the one of the good technique, so that we can get a alternative fuel. Also we can get biochemicals from the waste materials. And this is all about of my talk to your presentation. I hope all of you, if you're listening, definitely you will understand something whatever I have shown over here. Actually, based on this liquid biofuel, one of my book is published in Valley. If you can see, it is available in also Google book. Some parts they are available. You can read it to get the fundamentals, and it shows how to start a research in pyrolysis. I hope you understood. Thank you for listening for a long time to me. Thank you so much.
Thank you, sir. It is very insightful talk about the pyrolysis. I think participant, if you have any question, you can ask. Fahim Ahmed, so if you have any question, please ask that. Fahim, are you there?
Yes, yes.
Fahim, I think Fahim is not there. Any other participant?
Okay, any questions? I am here to answer regarding this pyrolysis, whether it is a thermal, catalytic, blending, everything.
Sir, I have one question.
Yes, yes, please.
Sir, in your institute, so there is a lab set up for this pyrolysis or not?
Currently,
Yeah.
currently we have a small one,
Okay.
not a bigger size one, a small one.
So suppose if we do some if we do some pyrolysis of that plastic, can we do that?
Yes, yes, definitely, definitely. We have actually right now we have designed a microwave. I have designed a microwave one. So if you are using a plastic then it should the degradability should be less than 350 degrees centigrade. Then we can go for it.
Actually, nowadays a lot of medical waste are generated due to the COVID. So we are planning to do some kind of research.
Yes, yes, definitely I can help, no issue. For medical waste, I can suggest one thing. Since medical waste, plastic, except the plastic, we cannot go for pyrolysis process. We can go for plasma pyrolysis process.
Okay, okay,
Yes, yes, because medical waste is having so many limitations, we can't use it directly. So plasma pyrolysis is one of the best technique for getting not liquid product to get gaseous product like hydrogen, methane. That is suitable.
so do you have anything about that gas to liquid technology?
No, right now we do not have anything else.
Okay, okay. Thank you, sir. Thank you, sir.
Thank you so much. Thank you, Professor Mahapatra and Professor Kundu. Thank you so much for inviting me. It's a very interactive session. Thank you so much.
Yeah, thank you, sir. I think nobody asked any question. Means I think we can wind up there, sir.
Okay, okay. And there you can contact me if anyone is not asking questions. You can contact me through email. I can also my phone number is there. You can call also. I'll be able to
Okay,
answer. Definitely, I'll answer.
okay, sir. Okay, okay.
Thank you.
Thank you, sir. Thank
Thank
you.
you. Good night.
Okay, so participant, see you again tomorrow at 10:15. Right?